Mindsetters, welcome to today's Grade 10 Maths Show. Today we have a special revision lesson on functions. We have selected highlights from lessons shown earlier in the term to help you revise. Please post your comments and questions on our Facebook page on facebook.com/learnextra or on Twitter @learnextra so we can help you with your revision. You can also download the notes for today's show from learn.mindset.co.za or click on the link on our Facebook page. Now it's time to get on with today's lesson.
We're firstly going to look at question 1, which is asking us to draw a straight line. Here it's slightly different though because they've given us a restricted domain. Okay, so they say sketch the graph f of x is equal to 2x plus 1 with domain minus 2, 2. Now guys, remember when you're sketching graphs, there are lots of different ways you can do it. Well, a few different ways. The one way is you can plot points on a table, or you can use the gradient intercept method, but the one that we prefer, that's used more often to sketch straight lines, is the dual intercept method. So that's the method I'm going to use to draw this graph, but just bearing in mind that our domain is restricted from minus 2 to 2, because remember your normal domain on on straight lines is x is an element of real numbers. That's the normal domain, but now they've restricted the domain. Alright, now what that means is that your graph is going to start at minus 2 and it's going to end at x is positive 2. So that's going to affect the end points will be affected on your straight line. So your end points are affected by the restricted domain. And I'm going to show you how they're going to be affected in a second. Okay, on my number line system, I'm going to put a few points on so that when we sketch this we can easily plot the points. So let's just say that's 1, 2, 3, 4, and then on the negative side we've got minus 1, minus 2, minus 3, minus 4. Now you'll notice I've gone way beyond minus 2, but you'll see that when I draw the graph we're not interested in anything that happens to the left there, and neither are we interested in anything that happens to the right, because they've given us a specific point that or specific domain within which we need to stick. Alright, and then we've got y is 1, 2, 3, 4, and then the same thing going down, minus 1, minus 3, and minus 4. Alright, the first thing we're going to do, guys, is let's look at what happens to this graph. F of x is equal to 2x plus 1. What happens at the end point of minus 2 and 2? What's going to be the output value? So we're going to put in minus 2, see what we get as an output value, and then we're going to put in 2 and see what we get as an output value. So I'm going to say on the side here, f of minus 2. So I want to get my end point sorted out. F of minus 2 is going to be 2 times minus 2 plus 1. So that's going to give me minus 4 plus 1, which is minus 3. So in other words, the x value at minus 2 gives me a y, an output value of minus 3. That's my function value on this graph. Now, remember you dealt with interval notation. The square bracket, that means including the end point. And then the round bracket means excluding the end point. So if I were to represent this minus 2, minus 3, it is an endpoint that's included when I represent it on the graph. Okay, so that coordinate is an included, in other words, closed dot coordinate. Alright, then let's look at what happens at an x value of 2. So I put 2 into my function and I get 2 times 2 plus 1, and that's going to give me an output of 5. Alright, so my other endpoint coordinate is x is 2 and y is 5. However, if you look at the domain, you will see that that point 2 has been excluded. So therefore this endpoint will have an open dot on your straight line to show that that point has been excluded from the domain. Alright, now how would we normally, so we're going to keep this in mind, we're going to come back to that. We're going to use the dual intercept method to sketch the graph as we normally would do. Okay? And then obviously take into account or factor in the fact that we have a restricted domain. Alright, so we've got f of x is equal to 2x plus 1. Alright, so the first thing we do, find the x-intercept. To find the x-intercept, you let y equals 0 and you solve for x. So therefore I'm going to get 2x plus 1 is equal to 0. Therefore 2x is equal to minus 1 and x is equal to minus a half. Alright, so your x-intercept is minus a half. So your coordinate there, minus a half and 0. Alright, then we find the y-intercept, and we find the y-intercept by saying let x equal 0. So if we let x equal to 0, we're going to get f of 0 is going to give me 2 times 0 plus 1, and that's going to give me a value of 1. So therefore my y-intercept is 1. Alright, so we would normally plot those points on the coordinate system and then sketch your graph, drawing the 2 dots. So we've got an x-intercept of minus a half, alright, which is there, and a y-intercept of 1. Okay, we will then take our line straight through those points, right? So we would do, alright, I don't want a graph that's got dashes in it, so we're going to just get rid of that one and use a full solid line. Alright, so that would be your line. But now guys, remember you would normally then go and put arrows in at the end of these graphs to show that it goes on forever. However, we've got these two things happening. We've got a restricted domain. So this graph only exists for us, for what we've drawn it for, between the points minus 2 and 2. So the graph is not going to go beyond those 2 points. Alright, I'm going to stretch this out a little bit more so that we get, there we go. Alright, so that's what you have. So we've got at minus 2, the y value is supposed to be minus 3. Alright, and I'm just going to stretch my graph out so that it makes more sense in terms of the scale. So at x is equal to minus 2, we've got a y value of minus 3. That is an included point. So therefore, at the end of this graph, to show an included point, we would put a dot. So it starts from x is equal to minus 2. It goes up until the point x is equal to 2 and y is equal to 5. And that end point is excluded. So you would end your graph off with an open circle. Alright, so with a restricted domain, you've got to take into account what the end points of your graph is doing. Okay, you use those x values to work out your function values, and then you restrict your graph by either using closed dots to show an included point or an open circle to show an excluded point. Alright, hopefully you're all with me and you have been following and you understand how to deal with restricted domains. It's really drawing a straight line as you would normally do, except for bearing in mind that the restricted domain is going to cut the graph out. So you're literally looking at a segment of the graph. You're not looking at the entire straight line. All right. Okay, so we're going to move on to hyperbole, and this is now question 2. We are asked to draw the graph of g of x is equal to 4 over x. And then we're going to use that graph and explain how the graph h of x is equal to 4 over x plus 2 compares to the original graph. We're then asked to draw h of x, which is this new graph 4 over x plus 2, on the same set of axes as g of x, and show all our asymptotes and the points of intersection with the axes. Alright, now the graph of g of x is equal to 4. G of x is equal to 4 over x. First thing we do, guys, we look at the value of a. We know that a is greater than 0, right? So that tells me we're going to have, just a rough sketch, if a is greater than 0, your hyperbola is going to fall in the first quadrant, and the third quadrant, because that's the product where your product of your x and y values are positive. So we're going to have graphs within the first quadrant and the third quadrant. All right, we know that everywhere, because remember, you can cross multiply this. So if you have y is equal to 4 over x, we can cross multiply and rewrite the equation of the hyperbola as xy is equal to 4. So what that means is the product of the x and the y values will give us 4 anywhere along that curve. All right. Also, we know that x is equal to 0 is our vertical asymptote. Okay. And we know that y is equal to 0 is our horizontal asymptote. So in other words, the axes are asymptotes to this graph 4 over x. All right, so that means the graph cannot touch those lines. Okay, we know that it's a positive graph, so we're going to have a graph in the first and in the third quadrant. And as you can see, these graphs go away from, they approach your axes, but they don't actually ever touch the axis. So this is y is equal to 4 over x, or g of x is equal to 4 over x. Okay, so that's your basic standard graph. All right, that all of you have seen before. They then say, explain how the graph h of x is equal to 4 over x plus 2 compares to the original graph. Now guys, remember we discussed this in the beginning. So what we've done here is we've changed the value of q, and we've discussed what happens when you change the value of q. Your value of q is going to imply a vertical sliding, a vertical movement of your original function. All right. So in this case, because q is positive, it's positive 2, therefore our graph is going to move 2 units up. So it's a vertical movement of the original hyperbola, and it's going to move 2 units up. So that's how they're saying, explain how the graph compares to the original graph while it's going to move vertically upwards by 2 units. That's the graph of h of x. Okay, so that's what we understand is going to happen to the graph. All right. They then say, draw h of x on the same set of axes as g of x, showing all asymptotes and points of intersection. So h of x being that. All right, so we've got h of x is equal to 4 over x plus 2. We analyze the graph once more. We know it's basically going to be the same graph shifted up 2 units. But if we were just given this question, asked to draw this graph, we would analyze it from scratch, right? We'd look at a and we'd say, well, a is greater than 0. So we know that that means it's going to fall in the first and the third quadrants. All right. We then look for the x-intercept or the y-intercept. Let's see if we can find any. All right, remember we are dealing with a hyperbola here. So if I were to look for, say, we're going to look for the y-intercept. Okay, and all of you should realize this already here. If we were looking for a y-intercept and we said x is equal to 0, guys, what's going to happen? If I substitute 0 in place of x, I'm going to get an undefined value because I'm getting 4 over 0. So this whole thing is undefined. So therefore, these hyperbole, remember, they're never going to have y-intercepts. Okay, because every time you substitute an x value in there of 0, you're going to get an undefined equation. So therefore, we say x is equal to 0 is a vertical asymptote. All right. We then, if we try to find an x-intercept and we let y equal to 0, again, we're going to end up with an asymptote. You're going to get a graph that's discontinuous when y is equal to 0. Because also, guys, remember, we've said at the outset, when you've got a hyperbola of the form y is equal to a over x plus q, the value y is equal to q is your horizontal asymptote. So therefore, my other asymptote, my horizontal asymptote, is y is equal to 2. Okay, so we need to put that onto the graph. All right? So we're going to have, okay, let's just get a nice color so that we can see it clearly. Let's use the green. So we've got y is equal to 2. That is the horizontal asymptote for the graph. Y is equal to 4 over x plus 2. So we've got a horizontal asymptote of y is equal to 2. All right? So therefore, if I tried to draw this graph, what's going to happen? Remember, we said already the graph's going to move 2 units up. So you're literally going to see a translation of the graph. It's going to slide up by 2 units. So all I'm going to do to recreate this graph is clone the original picture and then move it up by 2 units. All right. So we're going to get, let's have a look. All right, so we're going to have, this is my original graph, right, as you can see, and that's going to move upwards by 2 units. So that's what your graph's going to look like. So it's almost, as you can see, it's approaching the line y is equal to 2 like it did the x-axis. So that's your new asymptote. Okay, and then the same with this line, with this graph, sorry. It's also going to move upwards by 2 units. Okay, and again, not touch that graph. All right, so that's going to be the vertical movement of your graph. Y is equal to 4 over x plus 2, and it's simply all just slid up by 2 units. Okay, showing all asymptotes. So we've shown y is equal to 2 is the one asymptote, x is equal to 0 is the other asymptote, and we've shown how the graph moves up. It's a vertical shift of the original graph. All right.
Okay guys, I hope you are enjoying this revision session. If you need help, remember to post on the page or send an email to helpdesk@learnextra.co.za. Now it's time to take a quick break, but don't go away, we'll be right back. Welcome back guys, we have some great news to pass on to you. We will be bringing you winter school from the 30th of June till the 20th of July, starting at 10 a.m. every weekday. To get the full schedule, visit our website learn.mindset.co.za and look for the winter school link. Join us, it's going to be a lot of fun. But now it's time to get back to the lesson.
So hopefully some of that 76,000 of you are paying close attention to your screen right now as we start looking at exponential graphs, and we're going to go through sketching an exponential graph. In this case, we've got one, f of x is equal to 3 times 2 to the power of x plus 2. Let's go through the steps. During the break, I just drew up a rough axis there that we're going to use a little bit later on. All right, so the steps. First thing, let's look at the shape of the graph. So we've got f of x is equal to 3 times 2 to the power of x plus 2. Let's just make sure that is correct. 3 times 2 to the x plus 2. All right. We look at the value of a, guys, the coefficient here of the exponent, and we see that that is greater than 0. So straight away we know it's a positive graph. And what we said before, positive graph is going to curve upwards. It's an increasing function. All right, so that's what my graph is going to look like. I know what the shape is. Okay, next step. Okay, the order of the steps don't really matter. All that's important is that you get all the points down. So don't worry if at school, you know, you do the intercepts first, you do asymptotes next, you do shape last. As long as you get these steps in there, you will get the right graph. All right, so first we look at the shape, right? We know a is greater than 0, so I'm going to have an upward facing graph. Then I'm going to look at what the horizontal asymptote is. Now remember, your asymptote, the graph is not defined anywhere along that line. Okay, it's got no value along the asymptote. So the graph will never touch that line. The horizontal asymptote, remember I've shown you before, it's when y is equal to q. And in this case, the value of q is 2. So therefore here, y is equal to 2 is my horizontal asymptote. Okay? Now with an exponential graph, when we look at the y-intercept, if you remember, I've already shown you how you can get it immediately. To get the y-intercept, if you want to do it the long way, you say let x is equal to 0, and you can actually work it out from this equation by doing the whole thing. But we already know, right, from what I've shown you before, we already know the answer is 5 because it's a plus q. But just to go through the motions of showing you how you get it, if you let x equal 0, you get 3 times 2 to the power of 0 plus 2. The exponent 2 to the 0 is 1. 1 times 3 is just 3, and then 3 plus 2 is 5. So therefore my y-intercept is 0, 5. All right. Now many of you have already done exponential graphs, so you know that there's no point in going on to find the x-intercept, but I'm going to show you anyway. To find the x-intercept of this specific graph, we say, well, generally of all graphs, but the x-intercept for this specific graph, you should know, does not exist, right? But let's go through it. So x-intercept, we let y equal 0, so we get 0 is equal to 3 times 2 to the power of x plus 2, right? Okay. The point here is to solve for x, your exponent. We're looking for the x-intercept. If I take my 2 over, I'm going to get minus 2 is equal to 3 times 2 to the x. Divide both sides by 3, you get minus 2 over 3 is equal to 2 to the power of x. Guys, no matter how hard you try here, there's not going to be any solution. Why? You're never going to be able to make these bases the same. You can't use any other method that you know in grade 10 or any other grade to solve this, all right? Because you can't have a negative base equaling a positive base. It's never going to happen. So therefore, there is no solution, so there is no x-intercept. All right, there's no x-intercept here. So we need to plot the graph using what the information we've got. We know that we've got an upward facing graph. We know that the horizontal asymptote is y is equal to 2, right? Y is equal to 2 is my horizontal asymptote. So that means at 2 on the y-axis, I'm going to draw the asymptote. Okay? So at y is equal to 2, there we go. We have our horizontal asymptote. I'm just going to extend it a little bit to the left. And let's mark down any of the other key points that we might have for this graph. We know what the shape is, right? And we know that the y-intercept is 5. So we've got an upward facing graph with a y-intercept of 5 on the y-axis there. We put that mark down. We know what the shape is, so therefore we simply join those together, join our points, and that's going to be our exponential graph. So this is y is equal to 3 times 2 to the x plus 2. Guys, you'll notice that when you draw these graphs, it is always a good idea to put down the name of your graph. Also clearly mark your intercept. Mark your asymptote. Okay, also, which I didn't do here, which I'm very bad at doing, but you need to always put in the labels on your axes. So, you know, the y-axis, the x-axis. Show the arrows showing the direction. Make sure when you draw these graphs, your asymptote and your graph, they should never ever join each other. You don't want them to ever intersect. If they intersect, you will lose marks because that is not correct. Remember, your asymptote and your graph will never meet. All right, so that's just the basic drawing. How do we go about sketching an exponential graph? Well, there we go. That's how we do it. We look for the shape, we find the intercepts, we find the asymptotes, and then we put all of that information together, remembering to label our axes, put down our asymptote on the graph, and also put in all of those key points like your y-intercept. All right. Hopefully all of you are with me and all of you knew how to do this one. Okay. Now we're going to move on to the next one, and this is a little bit of graph interpretation, which I know some students sometimes struggle with. So hopefully after doing this one, you'll be able to do our challenge question. All right. Graph interpretation is really just an application of all the knowledge you have about graphs thus far. Okay, so it might look scary when it's put together in one question like this, but we're going to break it down into manageable pieces. Okay, so we've got the graph of f of x is equal to 4 to the power of x, so that's your exponential function, and it's drawn on the graph. You can see they've written there f of x is equal to 4 to the x. They say g of x is equal to minus 4x squared plus q, so that's your parabola. It's a downward facing graph, therefore it has a maximum turning point. The points A, 0 and 1, B, 1 and 4, and C are given. Alright, so I'm going to just put down A is the point 0, 1, right? That's in our little purple dot there. B is the point 1, 4. Okay. Now, in your graph interpretation questions, obviously all of your questions are going to be based on this figure. Okay. Part A says, determine the value of Q. All right. Now, if you look at the value of Q, we've got y is equal to, where do we find Q? We see that it's part of the parabola equation. That's the one they don't know. They don't know what the value of Q is. In other words, where is the graph turning? Because remember from the beginning when I showed you, your turning point on your parabola will always be 0 and Q. So really what they're asking us for here is, what is the turning point of this parabola? What is the y-intercept of this parabola? Because remember, your parabolae are always going to turn on the y-intercepts. So we've got y is equal to negative 4x squared plus q. All right, and if you go up to your graph, examine what they've given you. Remember, they've given you some key information here. They've said A is the point 0, 1. So A is the y-intercept of both the exponential function and your parabola. So that's the point 0, 1. Right? So therefore, the value of Q being your turning point, being your y-intercept of the parabola, you can read it straight from the graph. The value of Q is 1. Okay. So that's quite nice and easy, straight from the graph, reading your answer and giving us the value of Q. They then say calculate the length of BC. Okay, now remember, we can now change this equation. It's minus 4x squared plus 1. If you're looking for the length of BC, okay, you can see it on your graph. That's the point. B is the point on your exponential function. C is a point on your parabola. Now these 2 points, you can see that they're joined by the same vertical line. That's very important, because if they are along the same vertical line, guys, what does that tell you? Same vertical line. That means the x value along this line is going to stay the same. So therefore, the x value anywhere along line BC is going to be 1. How does that help you? Well, we're looking for the length BC. So that's a vertical distance, right? Whenever you're trying to find a vertical distance of a graph, okay, and these points are on the same vertical line, it's always going to be top graph minus bottom graph. So in other words, the y value on the top graph or on the upper graph minus the y value on the bottom graph is going to give you the distance BC. So my y value at point B, the top graph, is 4. I need the y value at point C to determine the distance BC, but we don't have it. So how do we work it out? Well, importantly, they've given us the point X is 1 on this line BC. So if I want to find out what the point C is, all I need to do is substitute that value into my defining equation for the parabola, get the coordinates of point C. Once I've got the vertical point, well, the y coordinate at point C, I can then work out the vertical distance between B and C. Okay, so first thing we do is let's find out what the y value is when x is equal to 1 on the parabola. So at x is equal to 1, I'm going to substitute 1 in place of x, and I'm going to get minus 4 plus 1 is negative 3. All right, so therefore the coordinate now becomes 1 and negative 3. So point C is the point 1 and negative 3. Okay, remember we're looking for the vertical distance BC, therefore we had to first work out the coordinate at point C, the y coordinate. So my distance BC, the distance of BC is going to be the y value on the top, the y value being 4, minus the y value on the bottom graph. So it's going to be 4 minus 3, which is going to give me 7. So BC is 7 units. All right. Okay, that's quite a common question, guys, so make sure you understand how to do that. Remember, any graph, if you're looking for the vertical distance, they lie on the same vertical line. The x values are going to be the same, so therefore you can work out the y coordinates, say top graph minus bottom graph. So in other words, the y coordinate on the top graph minus the y coordinate on the bottom graph, the difference between those two will give you the vertical distance. All right, let's look at part C. They say give the equation of f of x reflected about the x-axis. Now, any point reflected along the x-axis. So, let's just have a look at something on the side here. If I take any points on and reflect it on the x-axis, so let's just say this is the point 2, 3, okay? Reflected exactly the same way at the bottom. Any reflection in your x-axis is going to mean your y values, the sign changes, okay? Because when you reflect along the axis, you're going to go from positive y territory to negative y territory. So therefore, your 2 is going to stay exactly the same because it's still on the same vertical, right? But your y value, you're going to change the sign. So any reflection on the x-axis will mean a different sign for your y value. Okay, so reflection on the x-axis means a change in sign. It's exactly the same the other way around. So if I were to take negative 3 and then reflect it along the x-axis, reflected, that would be positive 3. So it's the same with the graph, right? If you're going to have f of x being reflected about the x-axis, it means all your positive y values are going to become negative and vice versa. All right, so f of x is your graph 4 to the power of x. So simply now, the reflection, did they ask us to call it anything specific? No, they just said give the reflection. So the reflection is going to be, this is on the x-axis, it's going to be y is equal to negative 4 to the power of x. Okay, so the graph is just going to be reflected along the x-axis, so therefore we change from positive y values to negative y values, as you can see there. All right, so y will be negative 4 to the power of x. Okay, let's move on to part D. They then say give the equation of f of x shifted vertically upward by 1 unit. So they've given us a lot of information there. It's moving vertically. Okay, that means straight away in your head, it's affecting the value of q. It's moving which way? It's moving upward. So therefore, it's a positive change. So it's moving upward by 1 unit. They say call that h of x. So they're taking the graph of f of x, right, which was 4 to the power of x. We're then moving it upward by 1 unit. So therefore, we're adding 1 to every single y value. So my new equation will be h of x is equal to the original function f of x plus 1. Okay. All right, and then think this is the last one here. 2 more. What is the equation of the asymptote of h of x? So now we've got this new function h of x. We've got h of x is equal to 4 to the x plus 1. The equation of the asymptote, remember, it's always going to be y is equal to q. So y is equal to 1 will be the asymptote of h of x. And then finally, part F, find the range of g of x. So here we're talking about the parabola. Now guys, remember, whenever you're talking about the range, you're dealing with the set of y values, okay? When you're looking at your parabola, right, it's either going to be all values above a certain value when you've got a minimum turning point, or it's going to be all the y values below a certain value when you've got a maximum turning point. So your range, if it's not restricted, if your graph is not restricted in any way, it's always going to revolve around the turning point. It's either going to be greater than q or less than q, all right? So if we look at our graph, g of x here, minus 4x squared plus 1, okay, we can see, look at what's happening. The graph turns away at the point 1 on the y-axis. So therefore, you can never have a graph, a point, greater than 1 anywhere here. Doesn't exist for the parabola. The parabola stops at 1. So therefore, your y values are everything less than 1. So your range is going to be y is less than equal to 1. Okay. Or, writing it in interval notation, y is an element from negative infinity. So that means all the values below, starting all the way down. It's all the way from negative infinity up to the point 1. If you want to write this in interval notation. Up to and including, so that should be square brackets. All right, so y is an element from negative infinity to 1.
I think it's time for a break now. Don't go away. We'll be right back. Welcome back from the break. Let's not waste any time and get straight back to today's revision lesson. Over to you.
All right, guys, so we're carrying on with trig graphs, and now we're looking at some of the questions. Question 1 says, draw a sketch graph of y is equal to tan x plus 1 for x an element from 0 to 180. So what have they given you here? They've given you the domain 0 to 180. Please do not confuse this. Domain is not the same as period. Okay, remember the domain is just the range over which you're sketching the graph. So it's the set of x values for which you're sketching the graph. The period is how long it takes to make that specific graph or that specific function, trig function. All right. Now I've just drawn up an axis here. Remember, with your tan graph, you're going to be working in intervals of 45. So I've put down the rough points that we're going to need. You also will need to show on your graph where 45 and 1 is. Where's it going to touch your graph? All right. So I'm going to just quickly fill in other things on our axes. We've got 45, 90, 180. We've also got a value of 1 there, and let's put a minus 1 down here. Okay, so those are points that I want to include in my graph. Now, guys, we're looking at a vertical shift here. We've got tan of x plus 1. Okay, so that's a vertical shift of tan x up 1 unit in the positive direction. Okay, so what we're going to do is draw the normal tan x graph and simply move it up 1 unit. Okay, because remember, when you're saying tan x plus 1, all of your function values, all of your y values are really, you're just taking it and you're adding 1. So it's literally just shifting up by 1 unit. So the distance between the original tan x function and tan x plus 1 is going to be 1. All right, important things on the tan graph. We first need to write down our asymptotes. Okay, and if you were paying attention from the previous summary, you'll see that x is equal to 90 is an asymptote, and x is equal to 270. However, guys, we are only sketching over the domain 0 to 180. So that means this one is going to be outside of the domain that we're looking at. So therefore, we don't have to put that specific asymptote in because it's not going to be on our graph. It's not going to be for the specific period, specific domain. So therefore, x is equal to 90 is the only asymptote that we are interested in. All right, and we know that at x is equal to 90, the graph is undefined. So at 90 degrees, okay, which is there, I'm just going to move that down, going straight through 90, we're going to have our asymptote. Okay, and then if this graph went on, if they asked us to sketch it from 0 to 360, there obviously would have been the other one at 270, but we're not interested in that portion of the graph. So our graph is really just going to stop at 180. So we don't need this continuation of the axis. Hey, it's just going to stop at 180 degrees, which is going to be, there we go, somewhere there. All right. So you only draw, guys, if they give you a specific domain, you're only going to be interested in that part of the graph. You're not going to draw all this extra stuff from 180 to 360. We're only interested in this little portion, okay? So that's our y-axis, that's the x-axis. We know that that's the origin, that's the point 0, 0. All right? Remember, an important point on your normal trig graph is tan of 45 is equal to 1. This point, this coordinate, you need to show on your sketch graph. Remember, it's a sketch graph, so you're not doing point by point plotting. You're putting in the key or vital information. 1 and 45 is one of the things you need to show on your tan graph. So tan, when x is 45, tan of 45 is 1. So that means when we draw the normal graph, remember I'm not drawing tan x plus 1 yet, I'm just drawing tan x, and we're going to move that. All right, so that's the first little section there. And then we know that it cuts the y-axis at 180 and 0. Again, and it's going to come approaching your asymptote at x is equal to 90, never really meeting that asymptote, right? So therefore, we've got our key points. We know that at 0, the graph is 0. At 45 degrees, your values there are 45 and 1. At 180, it's 180 and 0. And then if you wanted to put one more key point in at 135, the graph is minus 1. Okay, so that's your original graph. Now, we're going to take that graph, right, and we're going to move it upwards vertically to get this graph. So this is my original graph, this graph in pink. All right. All I'm going to do with my vertical shift is I'm going to move the original pink graph up 1 unit. So let's see if we can just clone this graph here. Okay. All right, so that's your original graph. You can see they're on top of each other, right? I'm going to simply move that graph up 1 unit. So guys, it's no longer going to start at 0, 0. Now, where's it going to start? It's going to start at 1 and 0, because we're moving it up 1 unit. Okay, and I want to try and show you as far as possible so that it doesn't look like those two are intersecting. But we're going to move the graph up 1 unit so that the distance between the two graphs, that distance there, needs to be 1. Okay, my graph is not drawn accurately and to scale and so on, so therefore you can't really see nicely, but that distance there has to be 1. They mustn't intersect. Okay, the difference between those two graphs needs to be 1. So you simply take your first graph and you move it up 1 unit. I'm saying the same thing over and over again so that it sinks in and that you guys understand, right? Again, let's do the same thing. So we clone the first pink graph. Okay, that's it, sitting on top of each other. What are we doing? We're moving that graph up 1 unit. So instead of it being 180 and 0, it's now going to be 180. We add 1 to 0 and we get 1. So therefore, your graph again is moving up 1 unit. Okay, I'm trying to keep this as steady as possible so the graphs don't intersect, and I hope we don't lose any accuracy in it. There we go. So therefore, the distance between the two at the bottom, remember this is still part of the same tan x function, that distance should be 1 unit if you move it accurately. Now remember, this is what I'm saying to you. If you look at your end points, and I'm going to go over the tan x plus 1 in yellow so that you can see what's happening clearly. Okay, so the graph's in yellow, that is our tan x plus 1, and all we've done is we've simply taken the original function and moved it up 1 unit, and that's how you expected to draw these graphs in school in the grade 10 level. You're not going to do point by point values and use a table and that. You need to know your key values and then use that original tan graph or your original cosine graph and then either move it or stretch it or shrink it or whatever the case is. All right, and then remember guys, you need to show those key points. So I've shown you on the pink graph, 45 and 1 was the original point, but on your new graph, you also need to show that key point is now going to be no longer 45 and 1, it's going to be 45 and 2. Okay, so that's a key point on your new tan function. Okay, similarly at 180, it's no longer 180 and 0, it's moved up to 180 and 1. Okay, all right. Hopefully you're all with me, you all understand that. Key points for you to remember on the tan graph. Remember to get your asymptotes. Remember to put in your value at 45. At 90, you need to put your asymptotes. At 180, you need to have your x-intercept, and at 0, you need to have your x-intercept. And at 135, you can put in the point -1. So those are the key points you need to draw the tan function. Please don't put in every single value. It's going to take forever. It's going to take way too long for what this question will be worth. All right. Okay. Let's move on. So this is question 2. Okay, this one's slightly longer. Here we asked to sketch the graphs of f of x is equal to 2 sine x and g of x is equal to cos x minus 1. They're on the same system of axes, so we need to be a little bit careful here. X is an element from 0 to 360, so that is our domain, not the period. Okay. So let's put in some values, some key points that we will be putting on the sine graph and the cos graph. Okay. We know the value 0, 0, that's at your origin, so that's 0, 0, where the axes intersect. And then we've got the values for 90. We know that sine of 90 is 1, so if I just label these, I'm going to use each of these as 30, so that's 30, 60, 90. So we'll say that's 90 there. Okay, and then that's going to be 120, 150, and then this will be 180. All right. 180, we're going up in sets of 30. 180 plus 30, that's going to give me 210, 240, 270 at that little square there. 270, 300, 330, so that will be 360 there. Which means I can reduce my axis just to what we are interested in. Okay. All right. Well, it's completely locked. Let's unlock it and hope for the best that it doesn't move everything. Okay, the whole thing is moving as 1 unit. So let's scrap that idea. Leave it as it is, but know that we're not going to be interested in anything beyond the point 360 degrees. All right, so we're stopping at 360, which is this little dot there. Okay, so that's the portion of the axis that we're interested in. On our y-axis, we know that we can see that the sine graph is going to go up to the point 2. So we're going to say that that is going to be 1. And so 1, 2, 3, 1, 2, 3, and that's going to be the point 2. Similar thing going down. 1, that's going to be -1 and -2. Okay, so we have an idea of what our axis is going to look like. Okay. For the 2 sine x graph, okay, you're simply taking all of your key points on your sine graph and you're timesing them by 2. So your function values are being multiplied by 2. Remember what I told you before. A is greater than 1, therefore your amplitude is going to increase. It's going to stretch the graph, all right? Your key points on your sine graph, we know that at 0, it's 0, all right? At 90, your normal sine graph is 1. Okay, we know that it cuts the x-axis again at 180, and then the minimum points at 270 is -1. I'm trying to keep that in line going across, and then at 360 the graph comes back up to 0. So we've got x intercepts here of at 0 and 0, and then at 180 and 0, and then we've got at 360 and 0. All right, so my original sine graph is going to look like that. All right, now if you're taking that graph and you are then timesing each and every value by 2, guys, what's going to happen? Those key values are going to stretch out, right? So 0 times 2 is going to give me 0. That other point, the starting point, your first intercept, 0, 0, from 0 to 360 is going to stay at the same point. Instead of plotting 90 and 1, we times that by 2. Sine of 90 is 1, times by 2, so at 90 degrees, we're now plotting 2 units, okay? 270, we know that the y value is -1, but we're going to times that by 2, so we're going to get a point at 270 and -2. All right, and then 360, 0 times 2 is going to stay as 0. All right, so therefore my new graph is going to be a stretched version of the original graph. Okay, so the graph in green is the one I'm interested in, and you can see that vertical stretch between the blue graph and the green graph. All your amplitude has changed, your graph has been stretched out. Okay, and I'm just going to delete the blue graph because we really don't need that blue graph. Okay, let's cut that out. There we go. All right, so we're just interested in the graph in green. And take out those points there, and let's neaten it up just a little bit there, and then here again. Okay, so that's the 2 sine x graph. So this is y is equal to 2 sine x. That's that first one that they've asked you to sketch, which we call in green, that's f of x. Okay, then we've got g of x is equal to cos x minus 1. So what are we doing there? We're taking the original cos graph and we're moving it down 1 unit. Okay, so your normal cos graph, what does it look like? We know that it starts at the point 0, 1. All right? What else do we have? So we have cos of 0 is equal to 1. Cos of 90 is 0. Cos of 180 minus 1. Nothing's happening to the amplitude here. There's no multiplication sign. There's no coefficient, in front of the cos. So therefore, it's going to stay at exactly the same function values. We've got cos of 270 is 0, and then cos of 360 goes back up to 1. So I'm going to draw the original cos function and then move that. What do they ask you to do? Move it down 1 unit. So it's a vertical shift downwards. So that's our original cos function. And guys, we simply now, in order to sketch cos x minus 1, we're simply going to take that graph and minus 1 from all the points. So if I take this graph, I move it down 1 unit. So it's simply going to do that. Okay, just a little bit more. So there we go, touches the axes. There we go. So that's your cos graph, which has been moved down 1 unit. So this is the graph g of x. All right. All right, so just to go over that again, reiterate, reiterate, reiterate. That's what we've got to do so that you guys remember those important points. You simply take your original functions. In this case, we took the 2 sine x graph times the original function by 2 to give us our graph in green, which is now f of x. for g of x, which is cos x minus 1, we took the cos x graph, which is now in pink, and we subtracted 1 to show the vertical movement downwards.
We've come to the end of today's show. Thanks for joining me and for chatting to me during the show. Remember to visit our website, learn.mindset.co.za, to get the notes and to watch the videos from the term. Goodbye.